Hello, everyone. Thank you so much for having me. My name is Mateen Malik, and I'm an industrial PhD student at Rice. So today I will present our method, that is simulation-based fault and attack injection at system level. So these are roughly the points that I will talk about today. So the first one is basically simulation-based fault and attack injection on system level. So I'm planning to present on a high level the importance and the validity of simulation-based verification and validation on a system level, and also at the same time introduce the method that we will be working on, or we are working on already. After that, I will be presenting sumo-based fault and attack injection, uh, and then the idea is the same, that I will introduce the method and also provide some demo. One thing to be noted here, that this is mostly focusing on the vehicle part of fault and attack injection. Then I will present the Sumo veins-based fault and attack injection that focuses on the communication level fault and attack injection. And the idea is to introduce the method and also provide some demo of it. And finally, the try to have some minutes for the discussion. So the time I will spend is approximately 15 minutes for the first part, 10 minutes for the second part, and 5 minutes for the last part, and then 5 minutes for the discussion.
Thanks.
Great. So as you already have maybe have realized, that I have used some terms here, which can be the name of the tools or the method itself. So I think it's a good idea to present the definitions of those terms that I've used here, because I will be using these terms later in my presentation. Sumo is basically simulation of urban mobility, and it's a free and open source traffic simulator. It was available since 2001, and it's a microscopic traffic simulator where each individual has its own attribute. So those include the road vehicles and public transport and pedestrians. Vanes is basically also a free and open source framework for running vehicular network simulations. And Vanes is based on the two simulators. One is OMNet++, that's an event-based network simulator, and Sumo that I have already talked about. So in Vanes, it is possible to model the inter-vehicle communication simulations. So in various industries, the areas where lots of investments has been made and will define how our future looks like. Those are automation, connectivity, and electrification, etc. This brings many advantages to the society, of course, but at the same time increases the risk to the automated and interconnected safety critical systems. The risks are basically the development and operational faults, and also the security threats, such as the intentional attacks to compromise the system. So the importance of verification and validation of these areas have also increased at the same time. Our method is applicable within automotive domain here, uh, and will facilitate the verification validation by injecting faults and attacks. As our use case is within automotive domain, so I will focus on it in the coming slides. Okay. So here it's the verification and validation stages, or also called integration steps, that mostly are in use or for the within the automotive industry to verify and validate a system. In this case, it's a vehicle, for instance. So the first starts with the simulations. In simulations, it could be software in the loop simulations or model in the loop simulations. And then one main property of this stage, that there is no hardware involved in at this stage, and the software is developed using simulations, as well as it's verified and validated using simulations as well. Then in the next stage, that's the bench. In the bench, it is a mix of hardware and the software. The uh, the focus is basically on a particular ECU and the functions residing in the ECU. So all the simulation environment built around it, that is specifically for the base software verification and validation of a certain ECU. So this is the basic hardware in the loop system that we can say. In the next stage, the hardware in the loop comes in. This is a little bit more complicated. It has multi-domain systems. For instance, in the automotive, it could be the steering system, braking system, active safety system, etc. So it's possible to integrate those in this hardware in the loop stage. So here, the dynamic functional testing can be done, which means that we can run the scenarios and that can actuate or activate certain functionality, and we see if the functionality is according to the requirements or not. Um, then comes the test track. So in the test track, it's basically a complete system. So it's a whole vehicle with all the integrated ECUs and the vehicular dynamics, etc. And then the purpose is to test some subsystem or a system or some function in a controlled environment. Same goes to the field testing, that is in the public road, but the environment is controlled and the system is verified and validated in the field test. Finally, it comes public road testing. So mostly the certifications are done. Actually, they can be done on test tracks as well, but they can also be done on a public roads, especially in the case of autonomous drive systems. So here the purpose is that to run a system without any faults and errors in the system for some amount of time, to make sure that the product is safe and secure before releasing it to the end customer. One thing that is to be noted here is that every stage is also starts from the simple simulations, for instance, here to the complex level. So you see these white lines here, and that represents that the verification and validation of each stage, it never stops when the next stage verification validation in the next stage starts. So in case of simulation, it can, as I said before, that it can be used for a simple verification of very simple functionality in a very early development stages, or it can also be used later in the later development stages when we are also doing the field testing. So it's kind of a feedback loop here, and the complexity increases in the horizontal domain as well. So this was more or less the overall view of the verification and validation stages needed for a vehicle. But we will be focusing on this stage, the simulation stage, where the system is simulated, no hardware is involved. But as I said before, as we move up into the ladder, so the more hardware is added to the system, and eventually it's a complete vehicle. Moving to the next slide, so to highlight the importance and validity of verification and validation in the simulation environment, I thought it's a good idea to present this three-pillar approach that is proposed by OICA. OICA is the voice speaking on automotive issues in the World Forum. And OICA members represent the global auto industry, basically, that drives economic progress. Then GRVA. So GRVA is the UNECE Working Party on Automated, Autonomous, and Connected Vehicles. So OICA has proposed a new innovative certification schemes because, as I said before, the complexity for the automated systems, in this case autonomous drive system, has increased a lot, and a new type of certification scheme is needed. So here the proposal is about the three-pillar approach. This is needed for demonstrating the level of safety and reliability, which allows for safety market introduction of automated and autonomous vehicles, both AD and ADAS vehicles. So AD is the autonomous drive system level 4 and 5 SAE levels, and ADAS is the assisted driving active safety functions basically. So the whole idea behind this is to perform bulk of testing in the simulation environment, which can produce comparable results with the actual testing, such as when the hardware is involved, and then move up to perform the physical domain that is basically, in this case, this and this, the real world and the test tracks. So the purpose of the GRVA, so these are the focus for us, that safety and security of automated driving system and connected vehicles. We want to devise some method which can ensure the safety and security of interconnected systems. Also, the validation methods for autonomous driving, VMAT, cybersecurity aspects, and within ADAS, this is interesting: remote control maneuvering and remote control parking, and automatically commanded steering systems, etc. So there is some text here as well, which tells that in order to reduce as we go up, basically. Okay, so Oika has also presented this table that actually where some of the requirements are mapped to the three-pillar approach of verification and validation that I have presented before. So no need to look into all 13 principles, but the most important ones for us are basically security and the safety of the system and function. So as we can see that the mapping here, that the so the proposal kind of agrees that if we want to test the security part of the system, that we can actually do in the simulation environment, and same as the functionality, the failure strategy, redundancy and redundancy concept, etc., into the simulation. And later on, here it's not crossed here, but maybe we could verify what we have tested here to the upper parts of the three pillars. Okay, so talking about the virtual testing or simulation, there are three main components that we need to consider. So the first one is the functionality. Functionality is basically what we want to test. Is it a system or a subsystem or a function? Within function, it could be an active safety function, AD and ADAS feature that we want to test, or any other thing, for some traffic sign information function, or it could be anything here. But we need to we need to know what we want to test. Then we need to have a vehicle, and then the parameters of the vehicle, like tires, chassis, and vehicle dynamics, etc., because the function is connected to the vehicle, and the vehicle is basically driven in the scenario. So scenario is also very important. So if we want to actuate some specific function in order to test the safety and security aspects of those function, we really need to think about what type of scenario we need and what type of scenario can actually actuate or triggers that function, and what scenario is dangerous or not dangerous for that specific function if something wrong happens in that function. So scenario has a big role to play when we want to verify and validate certain functionality. Okay, so as I said, like, our method will be used for fault and attack injection on system level simulations where the system components are simulated. So we are here in the simulation part, and we are using Sumo to create the use cases for verifying a certain function. So the result actually it verify the some capability of the vehicle, and we can categorize those capabilities into either it's a nominal capability or an extreme behavior of the vehicle in terms of faults and attacks. Okay. So I also wanted to give overall view of what test standards are relevant for us, or are also relevant for autonomous drive verification and validation in terms of safety and cybersecurity. So ISO 26262, it mainly handles the systematic end-to-end failures, random failures, and also talks about or recommends the safety culture of the system design. Then comes the safety of the intended function. This is mainly related to the nominal functionality of the function or of the it could be up to L5 functions, so L3, L4, and L5 function. How to make sure that the design that is created by the designer is safe enough, so the intended functionality is safe in itself. Then comes the cybersecurity part. So this, all the standards like 21434, it talks about the cybersecurity. So in our case, it's mainly touches more or less all these domains of standards. Okay, so now it's time to give an example, like what I meant, like when we want to simulate some use case in a simulation environment. So here in the autonomous drive system, in order to, so one more thing before I start explaining the scenario here. So this, whatever vehicle which is under test, that's we call ego vehicle, which in our case here is that red vehicle, and then there are vehicles which are the participants for the use case, or a part of the use case within the simulation environment. So those are the participant vehicles. Um, in case of autonomous drive system, there is one feature of ADS, which is autonomous drive system, is to keep the lane and make the maneuvering as safe as possible. So it kind of generates two paths at the same time. One is the normal path, which the vehicle tends to drive on, and the other is the backup path. And the backup path activates in case there is some emergency happens or some faults occurs that the vehicle cannot continue with the normal path. So it just activates the backup path and activates the fallback basically to safely and securely stops the vehicle at some point in the simulation. So what can we do here? So the maneuver is based on the sensors and the GPS input, that the vehicle understands its environment, where it is in the road, for instance, what's the heading of the vehicle and speed of its own vehicle and the other vehicles. So that is it actually, the ego vehicle use the sensors to get all that information or the GPS information. If there is any error in the sensors or any error in the GPS happens, then there is a possibility that the vehicle will not be able to continue the normal path, uh, or if there is a possibility that the vehicle um, some fallback strategy within this vehicle will activate. So the purpose of fault and attack injection is actually to analyze the behavior of the vehicle in terms of fault and attacks, and to make sure that the output in case of faults and attacks, the vehicle maneuvers safely, and also ensures the safety of the other participants of the scenario. Um, okay, so now it's our method that we are focusing on. It is simulation-based fault and attack injection on system level. I have talked about the simulation-based verification and validation, and I also talked about the importance of faults and attacks into the simulation. So the purpose, again, is to inject faults and attacks at system level to evaluate the system's dependability by injecting faults and attacks. Then the focus is basically on sumo-based fault and attack injection. So the focus is on the vehicle here, vehicle system, subsystem, or functions or sensors, and analyze the behavior of the vehicle or the surrounding vehicle as well under the influence of faults. Then comes the Sumo vanes-based fault and attack injection. Here, the focus is on the communication part of the vehicle. That could either be V2V, vehicle to vehicle, or V2X, vehicle to any infrastructure. And then analyze the behavior of the vehicle under the influence of faults and attacks. Then I would like to present the architecture of Sumo-based fault and attack injection that we have looked into. So in Sumo-based or Sumo traffic simulator, there are car following models, lane change models, road features, car attributes, and scenarios. So we can have all these by default, and there are some added by which are results of some really good projects. Uh, uh, so those models are added later into the Sumo Traffic Simulator. There is TraceEye, which is basically a short term for traffic control interface, and that give the access to a running road traffic simulation. It allows to retrieve values of simulated objects and to manipulate their behavior online. So in this case, in our case, we have a fault injector that we use TraceEye to connect to the traffic simulator, and the purpose of the fault injector is to inject different types of fault models, and also to define the location where we want to inject the faults, what type of faults, how long that the fault should persist, and also at what time we inject the fault injection time. Finally, in the architecture, it's a database which is used to log all the available parameters of the Sumo traffic simulator, or the specific parameters that we are interested in, and also some data or parameters that we would like to store or log from the fault injector. We have a paper already, so some of my colleagues, Mehdi Maliki and Berosh Sangcholi, they have already written a paper on this. So here is the source on the bottom: simulation-based fault injection in advanced driver assistance system modeled in Sumo. And that talked about this fault injector, which is also called SUFI, simulation-based fault injector. So please go to, so this paper has been accepted already, and if I am correct, the GitHub page will also be provided so that researchers can go in and just try the tool and see what we have done and if more can be done. So please go and read this paper if you are interested and want to know more about it. Okay, so just continuing with the Sumo. So as I mentioned, so Sumo has some models available that we can use. Those models include the ACC and CACC as car following models, and provide some mode speed control, gap closing control, and collision avoidance features or modes. On top of that, it also provides the lane changing model and intersection models. There are some other models also available that I haven't mentioned here, but those are such as Kraus and IDM. Those are the default models within Sumo. Okay, so scenario, I've already talked about the usefulness or the importance of the scenario, and that's also is the same in the Sumo scenario. So we really need to think about what functionality we want to test and what type of scenario we want to have. Because when we talk about the scenario, there can be millions and millions of scenarios that we can create, and that can actually verify and validate a very specific part of the function or a system. And we need to make sure that how much scenarios we need in order to fully verify and validate a system. If not fully, then at least to verify and validate to an extent which is acceptable by the end user and by the certification authorities. Okay, so I think now it's time to provide a demo. So this is the SUFI demo, simulation-based fault injector demo. So I will be showing you guys a golden run of the demo, and then the faulty run of the demo. So here, the first one is the golden run here. So you see there is a very specific use case where we have vehicles in specific settings, which are moving together with the ego vehicle, which is the vehicle under test. And then the vehicle tries to accelerate if there is enough gap between the vehicle in front or it will try to change the lane if there is an enough gap between the vehicle on the adjacent lanes. So we see what happens. So I just play these uh, video that we have recorded. Okay, so now the vehicle is moving in the middle lane, tries to go to the left lane. It has the indicators on, but you see the vehicle on the adjacent lane never allows that vehicle to change the lane because the minimum gap between the ego vehicle and the participant vehicle was not enough. So that's how the simulation ends. Now I will be showing you guys the faulty run. So the fault here is basically the fault in the gap and speed of the vehicle, which means in our case is that vehicle overestimates the gap and speed with the vehicle in front. And see what happens. Okay. So now it's a faulty run. So the simulation or the target time of the injection is 11 seconds to 21 seconds. So at that point, we have injected the fault, and we see that the vehicle couldn't maintain the gap because it overestimates the speed and the gap between the vehicles. So it kind of accelerates until it activates the emergency braking, and then there is a distance. Little bit increase between the vehicle, then it accelerates again, and then goes into the same situation and tries to do the same thing until the end of the simulation. Okay. So as I said, like we have been, Sufi is basically is very much focused right now into the Sumo. So Sumo is the environment where we can do lots of things with the vehicle, microscopic simulations, but there are some limitations in Sumo as well. Like if we want to have a really high fidelity sensors or sensor models, that is not provided in Sumo. The vehicle to vehicle and vehicle to infrastructure communication possibilities are also non-existent in Sumo currently. Also, the advanced vehicular dynamic models, advanced steering and braking models, which have been verified and validated by the real vehicle steering and braking functions. Um, and finally, there have been work ongoing, but we haven't focused a lot into this. But this is the area which can improve, and that is to integrate the machine learning-based autonomous drive stack, so that that can give an opportunity to actually integrate the AD stack into the Sumo and tries to verify the actual function, AD or ADAS function into the Sumo environment. So these are the some limitations that I want to mention. Okay, so now what we have done or what I have presented so far is everything on this level. That's the vehicle level, which is in Sumo. So if we want to extend the scope of our verification and validation, we can add or the another tool, Veins, that I have mentioned in my first slide, and that actually supports the inter-vehicle communication. So we can model different types of communications in Veins, and it is a kind of connected with Sumo as well. So now I will talk about the upcoming or the next verification method, which is Sumo-based fault or Sumo veins-based fault and attack injection. So this is the architecture that is presented in the website of veins. Here is the source here. If you are interested, just please go there, and there are more information present there. But here, briefly speaking, it is basically based on OMNet. That's the Objective Modular Network testbed, and also an IDE, and that actually gives an opportunity or possibility to integrate Veins. So Veins is the vehicles and network simulation. So it's a vehicular network communication framework, and that is connected to the Sumo traffic simulator. So all the vehicle mobility that happens in Sumo environment, and all the communication possibilities, like the modeling of the network layer or the physical layer or MAC layer, that is possible in Veins. So if we uh, induce or introduce some faults and attacks in the communication part, which resides here, then the effects we can see, if we want to see the effects on the vehicle, then we can see the effect in Sumo. So there is this, like, it's communicating bidirectionally by using the trace eye interface. Okay, so this is under development. This is Sumo Vanes-based fault and attack injection architecture. So here the idea is more or less the same. So as I said, that we wish to develop a framework or a fault injector that can insert different types of faults into the communication part of the whole system, which resides in the vanes part, and that is connected to the Sumo simulator as well for the vehicle mobility. And there is also a possibility to log anything from Sumo or vanes or even from the fault injector. So there should, this bidirectional, but there can be another line here. So this is approach that we are thinking to have, but this is still under development. But this is quite similar to Sufi in the appearance, at least. Okay, so then for the Sumo vanes based fault and attack injection, I think it's also a good idea to to provide an example as a demo that we have created for the platooning scenario. So the platooning scenario, there is the basic concept of platooning is that we have a ego vehicle, or we also called a lead vehicle, that is basically controlling the parameters of the following vehicle in a different way. It could be sequential, or it could be broadcast, or any other sequence that can have, but in this case it's a broadcast, you can see. um, then the leader vehicle defines different parameters like heading of the platoon, the speed of the platoon, the gap that needs to be maintained within the platoon, steering and braking, as all that, for instance, that is led, not braking, because braking is the gap, and then all the other following vehicles, they maintain the gap by accelerating or decelerating, and that is based on the sensors of each vehicles here. Um, so it's a simple platooning scenario where we can inject communication faults and attacks. So those, some examples of faults and attacks are replay attack that we can use, jamming attacks, or data injection attacks, etc. In, so that's how it looks like in the simulations. This is again a Sumo GUI. So here you see there is a platooning scenario established where we have the platoon leader, the first vehicle always, and then we have, in this case, 4 following vehicles. So I think it's a good time to see a demo for the platooning scenario jamming attack. So let me just play the video. Here there is, you see, it's the nominal platooning scenario, and at time 11 there will be a fault, a jamming fault, where there is no communication between the leader vehicle and the following vehicles. So of course in the simulation we see it just crossed, but in here you see it's a collision. So the vehicles kind of stop getting the information, so it couldn't tell if there is a vehicle in front or not, so it just keep on going and crashed into the leader vehicle. So that was a simple demo we wanted to show you, just for your interest, like how it looks like when there is some type of attack into the platooning scenario. And one more thing that I would like to mention here, that that was a sinusoidal scenario where the vehicle was accelerating and decelerating. So the attack when we have injected that was when the leader vehicles was decelerating. Okay, I think I've shown this. Next slide. Okay, so now what we have covered. So we have covered the vehicle part of it, that is Sumo based, and we also extended the scope of the verification and validation for faults and attacks, or for safety and security, into the inter-vehicle communication domain as well. So we have integrated vanes to Sumo. As I said before, there are some limitations in Sumo and that cannot be covered in Vanes as well. And that is if we want to have a really good high fidelity sensors, we can have them as well. And that we can have through Carla. So Carla provides better sensors. So we can look into what type of sensors Carla has and integrate those sensors into the system and then try to inject faults into the sensor part of it and see how the vehicle behavior will be. Um, okay, so my last slide is to summarize. I hope I didn't took a lot of time here, but summarize here. Summarization is I talk about the simulation, the importance of verification and validation in the simulation that is increasing. It has increased a lot lately, and now it is considered as a as a necessary part of the VNV, not just a necessary part of the VNV, but most verification and validation will be done especially in the automotive industry in simulation, which is representable with the original or testing in the real world. But those results will, of course, be comparable. I've also talked about the Sumo-based fault and attack injection and Sumo Vanes-based fault and attack injection. And I also mentioned a little bit of the future work that we can also extend this to where we have a real high fidelity sensor models in Carla that we can attach in the system and try to do some sensor fault and security based testing on the sensors. Yep. So I think it's time for questions. Thank you so much for listening.